Okay, good morning. Thanks to everybody for coming to our presentation entitled Integration of Multiple OpenStack Clouds with a Core MPLS Network. So what we really did here was build an Mpls Lab, a virtual Mpls Lab, and then sort of explore what OpenStack projects exist currently that can help to integrate more than one cloud into this MPLS core. So that was basically what we did for this one. So my name is Curtis Collicutt. I'm an OpenStack architect at InterDynamics. And I'll let Rahul introduce himself.
I'm Rahul. I'm a senior network engineer at InterDynamics.
So I always like to do a bit of a sort of front matter. We're standing obviously on the shoulder of giants, of all these people that have written code, like all these people who've written open source software, OpenStack. Also, we're the projects that we're using in this presentation, BGP, VPN, Bagpipe. Also, people who write and publish network labs, right? So we used some work that people have done to build our MPLS, our lab MPLS network. And books like MPLS in the SDN era, which you'll hear a couple times. It's a pretty fascinating book. I also like to give a little bit of perspective. So as an OpenStack operator, not necessarily a network engineer, I'm curious as to how we can build multiple OpenStack clouds and connect them together through some sort of core network, right? So how do I, as an OpenStack operator, like participate in modern networking, in automation, and then with this lab that we've built, we can then like observe how all of this stuff works, right? So we can, because it's all virtualized, we can like watch MPLS traffic on the virtual ports. We can run TCP dump and like see all the MPLS tags and like really start to investigate and understand how these systems actually work.
So why MPLS? We used MPLS because of the most of the devices understand MPLS. It's interoperable between different vendors, scales reasonably, and you can have MPLS can allow you to automatically configure the network settings for the tunnels and or the label switch paths, and many different kind of traffic you can run over MPLS without, it supports both the legacy network technologies and the latest IP-based technologies as well. And you can have a prioritization. You can prioritize the centers of traffic like VoIP, and it does traffic engineering and fast reroutes. So this is from MPLS in SDN era. And this, MPLS is not taken as an encapsulation. It's taken as a framework, like a control plane from data forwarding plane. It's decoupling the service and the transport overlay or the underlay. And for example, like in case of SP layer 3 VPN service, the PE can be like a layer 3 overlay, and whose underlay can be the SP MPLS core network. And it minimizes the forwarding state of the core, and you can have a multiple tenancy and multi-service on the edges by using that. So, and this is a slide from a guy from Twitter who says like, majority of the traffic, it's still on Twitter it's labeled, travels through MPLS. And it's just to emphasize, like, it's not the telcos only which uses MPLS in the core, but there are some other non-telco companies which do use MPLS still.
So when we're trying to connect multiple OpenStack clouds to some sort of core network, like we have options, and these are some of the options that we explored in this presentation, right? So like the first one obviously is that we just don't really do anything special. We just continue to use things like constructs like floating IPs and provider networks, and just really don't do anything. The next thing that we sort of explored is the Neutron dynamic routing project. So that's one option. After that, we looked into Neutron BGP VPN and the Bagpipe project. And those are the two that we sort of demonstrate in this presentation. But in the future, there's also a project called Neutron to Neutron. It's a spec actually right now, which hopefully will get implemented at some point. And then, of course, you have even more advanced systems like using SDN to actually do the to connect the clouds together. We don't explore SDN in this particular presentation, but these are the different potential ways that, and models that you could use to actually try to connect clouds through some sort of core network. So while we were doing this too, we realized that there's several places that MPLS could actually be applied. So like you could do nothing, you could announce routes, but the MPLS could actually be applied at the Neutron router or at the edge of the network. It could be at the top of rack switch, it could be in a smart NIC, obviously in the vSwitch or vRouters. Potentially you could have it in the VM, or maybe even all the way into the application, right? So we didn't explore those last two, but all the rest of them are definitely an option. So in terms of the MPLS lab that we built, what we did was kind of just do enough MPLS to have some sort of core network to connect OpenStack clouds to, and then work with that. It's based on a lab that was put together called Simple Juniper MPLS Core with L3 VPN. So we have 2 provider routers, 2 provider edge routers, and 2 customer edge routers. And then once we built that, we started to connect OpenStack clouds at different points and sort of see how this would all work out. Obviously, we're not intending to completely replicate some sort of massive service provider network. We just want to have some lab that we can begin to explore how we would actually integrate these things. And the nice thing, probably the most work that we did, was to completely automate the deployment of this MPLS simulation using Ansible and connecting to the VSRX routers using netconf, and it was all completely automated. I'll talk a bit more about that. So there's probably a lot of people in the room that are familiar with MPLS networks, but like when you start reading through the documentation about how this all works, what we find is that there's some basic constructs that are used. So I mentioned the customer edge, provider routers. So these are usually like abbreviated CE, PE, and P routers. There's also the ASBR and the route reflectors that are usually built into these networks in some capacity. We didn't use either of those pieces in this particular lab, but those are often things that you see with this. Also, being Canadian, we wanted to try to replicate like a large geographic network, right? So in our simulation, we pretended that we had routers in Vancouver, Edmonton, Calgary, and Saskatoon. We could also like apply, because everything was virtualized, we could use tools like TC in Linux to add latency to the links. So we could actually simulate that it's 20, 30 milliseconds between edges. So this is just a description of, a diagram of what our lab looks like. So there's the 4 MPLS, the MPLS core is kind of in the middle there. The dotted lines are indicating that it's an OSPF area. A big part of the automation for the development of this lab is we used the links as a way to build the inventory. So all of those sort of green circles with numbers in them, those are actually the links. And when in the Ansible inventory, we use those links to actually build what routers exist. So instead of, it's kind of opposite of what people would normally do, where it's like, okay, we have a bunch of routers, we know the inventory, let's understand what the links are afterwards. Instead, we started with the links and used some basic, just like a Python Ansible inventory to actually determine what the topology of the network would look like. And also you can see that we have a couple of OpenStack clouds connected. In this case, we've got them connected to the CE routers that are supposed to be in Vancouver and Saskatoon. So the first thing we're just going to kind of demo is just that basically that this simulation works, right? So what we're going to do is, because this is all virtualized, we can run TCP dump on the virtual interfaces, and we can actually watch the MPLS traffic go through them. And in this particular lab, because the MPLS paths are they're unidirectional, the echo, we're going to do a ping, and the echo is going to go one way, and the request is going to go one way, and the reply is going to come back another way. So all this is really doing is just showing that the MPLS network is actually working. So we're going to ping from the CE Vancouver router to the CE Saskatoon router, and then we can actually just watch the packets kind of go through. And so we can see that the request is going through one interface, and the reply is coming back completely through a different interface.
So Neutron BGP dynamic routing, one of the projects. So what was required for us, like how we can have the ingress access to the layer 3 tenants, VXLANs. The thing was, there was like next hop is not known for the, it's unknown for the rest of the infrastructure. This problem could be solved by putting a static routing, but there was manual intervention was required. So we use this project to automate the access to the tenant networks, basically. So in this project, what we saw is like the Neutron gets a BGP speaker, which speaks the which communicates with the rest of the BGP routers for like it kind of a CE, and it talks to the BE routers and acts as a control plane. So it's keep on anything new network spin up, it can advertise to the BE, and it can go to the other cloud as well. So, and the value was that self-service networks were readily accessible, and you can, as soon as you create it, you can see in a demo later on, like it would be showed up in the other cloud as well. So you can ping across, you can have a traffic across 2 different clouds. And it's not the same as a BGP VPN, which is, we will discuss later about that. And it doesn't have any plugin to integrate with Mpls directly, but Mpls could be in a core. So in the demo, we're going to show there's 2 OpenStack clouds, one on each end, and we'll create a router in Neutron and add it to the external gateway. And then as soon as we create a subnet in Neutron, it will be advertised through BGP speaker, and you can see the routes on the other end. And then we'll spin up one VM. It's going to be accessible from one cloud to another cloud. So you can ping it from one end to another end, basically. So demo. So here we have, so here on the screen we have like a CE on one end. This is, and these rights are already announced by BGP. And this is OpenStack Cloud 2, and we are now creating a subnet and a router. And as soon as the network is connected, subnet is connected to the router, it will advertise the routes through BGP speaker, and then you can ping the gateway from the other cloud, that is OpenStack 1 cloud. So basically here we are adding it, and you can see there's nothing, no routes yet advertised. So now we connected the subnet, and you can see the route coming up in the CE. PE router, sorry. Oh, CE SAS, sorry. And now from the OpenStack 1, you can actually ping the gateway, the newly subnet, created subnet. So we are pinging here the gateway. Now we're going to spin up one of the VM in OpenStack 2 and attach that subnet to it. It will get DHCP IP, and then you can see it would be reachable from OpenStack 1.
So it's kind of funny that they both got a .12, but they're actually separate IPs.
So here we are SSHing it, and it's accessible. And
this is where I can't type the password. Cubs win. So this is just a Ceros instance. So I can't type that either. There we go.
Yeah, so here's the IP which we access into. So now up to next project, Neutron BGP interconnect. And in this, we are trying to connect to existing BGP VPNs actually from OpenStack cloud. And if there are existing BGP VPNs, it could be in different clouds as well, but you can connect it to using BGP VPN interconnect. And in this, in OpenStack, it acts as a PE router. And you can have the VRF instances. You can share them through BGP. And this is the diagram, how it works, like an architecture diagram, a workflow. So here, there is like Neutron, on which you will create a network and associate one of the VPN route distinguisher. And it would talk to the backpipe drivers, and then it can talk to the Open switch. It can be OVS, it could be a Linux switch. And here, if you can see the backpipe BGP peers with the other peer members. It could be like with route reflector, or it could be directly with one of the peers. And there are two different things here. Like there's a OVS Mpls bridge, which acts as a data plane for the VMs to send their traffic and communicate. And backpipe acts as a control plane. So it's advertises all the routes, and it is like it's based on like IP VPN is their option. Then EVPN also you can use. And there are related talks in the summit regarding this BGP interconnect, which is by Thomas Maureen and BGP VPN for the edge networking. And there are some previous talks as well regarding the same.
So we've gone through Neutron dynamic routing. We've gone through Neutron BGP and bagpipe. So those are two projects that have code that exist, and you can actually use them to do this work. There's also work being done on something called Neutron to Neutron interconnect. There's a spec that's been written. There's no code that I'm aware of yet, but the reality is what we need to be able to do. If we have multiple OpenStack clouds, we need Neutron on both sides, or however many there are. We need those neutrons to be able to communicate together so that we can do routing across multiple OpenStack clouds, right? So there has to be some kind of API available for this to work, and this is something that this Neutron to Neutron interconnect spec could help with, right? So we need some kind of API to get this to work. Yeah, sort of reiterating that statement, but you know, as soon as we have we need an API to do this, and maybe this is one way that we can get that. So also we talked a bit about that there's the potential to use SDN solutions, and this is probably the way that a lot of organizations would actually do this. We wanted to first explore like what projects within OpenStack exist to do this, but obviously, you know, there's other ways that we can do this. So there's lots of different SDN solutions that are available. Kind of one problem with SDN and OpenStack is that if you step outside, if you use an SDN solution to do a lot of your work, and you step outside of the Neutron API, then you lose some of that interoperability that we like, especially in the NFV world, where we're using a standardized API to be able to do our work. So a lot of times if you use a SDN solution of some kind, you're going to talk directly to that SDN through its API. Now you've stepped outside of OpenStack and you're into, you know, a different API completely, so you lose some of that interoperability. Some of the examples that are out there, so Tungsten Fabric, Open Daylight, Calico, there's lots of different SDN solutions. I think there's quite a few talks related to what used to be, or Tungsten Fabric, which used to be called Open Contrail and Contrail. Tungsten Fabric is actually pretty fascinating because it heavily leverages MPLS already, right? So we didn't, in a future version of this talk, we'll start to explore some of these SDN solutions. We didn't do that for this quite talk, but it's pretty fascinating how well something like Contrail would fit into like a larger MPLS network. And you can see that the constructs that make up the Contrail solution are very similar to what, you know, an MPLS network would look like. So there's a few other related Neutron specs and projects. So one of them, and I'm not completely sure what the status is. I mean, mostly what I'm suggesting here is that people have been thinking about this kind of work for a while, right? So there's a Neutron BGP Mpls spec. You know, I don't know what its status is, but you know, it has the same kind of concept, right? Like, how are we going to connect multiple OpenStack clouds together, right, across some sort of WAN? There's a Neutron Edge VPN spec as well. Which has some of the same concepts and conclusions in it. And then there's a project called TriCircle, which is also trying to build some sort of Neutron to Neutron API. So building this lab, we learned quite a few things. So we heavily leveraged the Juniper VSRX to do a lot of the core network. But when and I haven't explored this fully as to why, but it takes quite a while for the VSRXs to come up when I instantiate them. So like, I can completely rebuild this lab using Ansible, but the time it takes for the VSRX to come up and then be available with netconf and then get configured can be up to 30 minutes in some cases. So I need to do some investigation there to determine what's actually happening. We also used all-in-one deployments quite heavily. So we're running most of this lab on a single hypervisor, right? So we used things like DevStack and some of the development deployments for various OpenStack sort of configurations. Through doing all this automation, though, it was really easy for us to just delete the lab, rebuild it, or move it to a different hypervisor, do whatever we want. You know, like it might take a couple hours for it to come up, but we could just completely delete it when we weren't using it and rebuild it in a couple hours. There's some to-dos that I would like to do in terms of automating that networking. So right now we're kind of hard coding IP address spaces. Like, I could probably add a little scheduler kind of to the Ansible inventory and start building that instead of having to fill out a bunch of YAML and determine all that. Also, we're using templates. So we're templating the Juniper configuration file, and that doesn't really that doesn't really work. And what we'd like to do is move to like a Yang-based model of some kind. So we have some work to do in that area. So I mentioned that the inventory that we use to build this lab is based on, it uses Ansible, but we built the actual inventory from the links that were defined. Instead of defining the VMs, we defined the links. And when you do that, we can actually use graphing tools to actually build a network diagram, because like I have sort of a thing against network diagrams. We want to be able to automate the creation of a network diagram. So this is like the kind of squiggly lines that you can't read. These are like a first attempt to actually build like an automated network diagram, using graphing libraries in Python and the link-based inventory.
So from lesson learned from Neutron dynamic routing, we saw that if the BGP DR agents is restarted, it loses the connectivity, and we haven't done that much investigation in this, and we were wondering how it can be implemented outside the POC thing. And the other thing was, you need to define, the cloud architecture guy or someone needs to define which networks they want to advertise to the connecting to service provider or PE routers. And in this Neutron dynamic routing, it's like it works on eBGP. They have a eBGP, so you can connect it to the different AS and how things work there. And then Neutron BGP interconnect. The major difference between two was one of the things like where we're going to place it. One, you can place it in the CE side, and this is acting more as a PE, not as a CE, but CE could be the VMs inside it. So, and it's based on iBGP, and you can. There's other problems with this Neutron BGP VPN. It's not a problem, but like some things like route distinguishers needs to be defined at the operator end. They need to configure that, and then you have to configure route targets where you can import or export the routes to other OpenStack clouds, which you want to talk to. So that was there. And yeah.
And then, so just to conclude, it was actually pretty fascinating when we started doing all this work. There, I realized about halfway through that there's an entire book, like a 920-page book, written on how to do MPLS in the SDN era, like literally. So this is a pretty fascinating book. I just couldn't believe that it exists. So this helped us out quite a bit. Some of the other things that we concluded from this is that, like, as I'm an OpenStack operator, not necessarily a network engineer, right? So networking has this long history of all these interop standards, and this is very powerful, but it also is quite a bit of stuff that I have to sort of learn and understand. I think as part of doing this, we discovered that, like we mentioned the CE, and we keep saying CEP and PE routers, but those aren't really that granular definitions, right? Like, depending on perspective, like, these things can have multiple roles. So I think, it's just not enough to just use those sort of, that terminology. We need something a little bit more granular. Also, we discovered that, like, we can stick an OpenStack cloud or some sort of MPLS piece almost anywhere, right? Like, so where we had them initially, like when we attached the DevStack nodes to a CE router, well, maybe that doesn't make sense. We could almost put them anywhere that we want, right? So where does it make sense to do that? We also, there's a big difference between doing this as a single operator with a single AS as opposed to inter-AS work, right? So there's a lot of interesting things that we could do in that area in terms of understanding how to connect multiple ASs together. However, the options for actually doing all this work are pretty few, right? Like, so we covered the two major ones, and we kind of need some additional work to be done in this area to use like an OpenStack only solution, right? So you could easily step outside and use a SDN and use its API, but it's a pretty slippery slope in terms of interop, right? So how can we do this using Neutron APIs of some kind, right? It was also extremely challenging to keep this dev lab up and running. I mentioned that we're using a lot of all-in-one instances, right? So we'd have a dev stack that's an all-in-one instance, or a tungsten fabric node that's an all-in-one instance, right? Like, most of these environments are meant for use in terms of like writing code. Like dev stack, you're supposed to use it to actually help you to write code. So we had some challenges in terms of like how do we build a small lab but not use like development instances, instant models. I think we concluded too that the intersection of this high-end networking and OpenStack, it's a pretty big technical domain, right? So there's not going to be a lot of people that have experience in both of them. So how do we find those people and sort of get them help them to work on APIs in Neutron for us? And ultimately, like, network integration of these multiple clouds is really about automating existing technologies that we understand quite well, like MPLS and BGP VPNs. Like, these are well-known constructs, and what we're really just trying to do is just automate their use, right? Provide some sort of API that enables us to automate the creation and use of these networks. So this is just a meme. Yeah. But I think one part that we didn't quite cover is that in the first solution with the Neutron dynamic routing, like the network owner, whoever owns the network, they would specify a particular subnet pool that cloud can announce, and that's all that cloud can use, right? So I think some people, when we showed this presentation to a few people, they're like, oh, well, like, would you really allow users to to automatically specify routes in your network? And you probably wouldn't, but you can limit what they can do by using the subnet pool, so it's not as scary as it kind of looks, right? So I just want to say thanks to Thomas Morin, who is one of the developers of BGP VPN and Bagpipe. He was a great help to us, so I really appreciate his help there. Also, we'd love to get some feedback. If there's people here that have ideas of how this kind of thing could work, please feel free to email Rahul or myself. And with that, I'll conclude and see if there are any questions. Any questions? Doesn't look like it. Okay, so thank you very much. Thank you for your time.